Hello, calculus students. This short video is about the integral application of finding the area between two curves. So if we have two curves, what's really the plan for finding this area in between them? And the area is always going to be a bounded region. I shouldn't say always, but for these particular problems that we're doing right now, it will be. P.S. Later you can find unbounded regions. But for now we're looking for this bounded, the area of this bounded region. So what is our plan? Well, if you recall what the integral does for us, it's an infinite adder. So I start with one representative rectangle and I look at its area, and then I infinitely add the ones from that end all the way up to the other end. And obviously they'll have different heights. They'll look more like this on this end and this on this end. But I find the area of one and then use the integral to sum all of the areas. So how do I find the area of one of those rectangles? And you always focus on just one. So the area of a rectangle like this is going to be length times width, of course. And our length in a rectangle like this is going to be the upper y value minus the lower y value. And the width is going to be delta x. So I multiply that by delta x. Now, since the delta x can't really change its looks, we make sure that in a situation like this that our functions for upper y and lower y are in x, so that we have an area function all in x. So I would have to take f of x and g of x. If g of x were my lower parabola and f of x was that upper parabola, I would say the area is f of x minus g of x, and those functions are in x, times delta x. So those are the areas, and it looks like these are my points of intersection. I'm just speaking generally here. I'll label those A and B. Of course, you can find those usually on a graphing calculator if you can't solve for them algebraically. So I would then take that area of the rectangle, I would sum up all of them. I'll say x pi and x pi there. I would sum up all of them from 1 to n, and then I'd take the limit as n went to infinity or as delta x goes to 0. And this is the definition, that limit of the Riemann sum is the very definition of the integral. So I have the integral of f of x minus g of x delta x from A to B. And that's generally how you do areas between curves when the curves are oriented this way. So let's take a quick look. Oh, also, I meant to mention that it won't matter if the curves are above or below or one above and one below the x-axis, because if you look at these, okay, let's take, you can see that that height is going to be 4, and that's like the one we just set up. But if you take one curve below and you have the height at 5 and another one at -2, then 5 minus -2 is going to be that 7 height, and that's really what you want. So the signs kind of take care of themselves. If you just subtract upper function value minus lower function value to get that height. Same thing here. -2 minus -6 for that height that we see right there is equal to -2 plus 6, or 4, which is that height. It's a positive value. Now keep in mind we are finding the area bounded by these curves. We're not finding the integral values, which could be negative. We're actually finding area, and area is always positive. So sometimes, the integral measures the opposite of that area if the function is below the curve. But in this case, we always find the area of that rectangle by taking upper function minus lower function and times delta x, or the thickness of the rectangle. Okay? So it will always work no matter where those curves are. So let's practice. Determine the area bounded by the graphs of f of x equals x squared, g of x equals the square root of x. And absolutely the very first thing that you should always do is graph these guys. So I know what x squared looks like. It looks like this. Sort of a general image. Okay, so that's my f of x. And g of x is the square root of x, and that looks like that. They are inverse functions for x greater than 0. So, we think about one rectangle. Always focus on just one rectangle right there. And we think about the area of one rectangle. Always stop, pause, and go, what's the area of that rectangle? And we take the upper function minus the lower function. The upper function, in this case, is going to be the g of x, or square root of x. So square root of x minus x squared. I kind of know this, the way the curves look. You might want to check a graphing calculator. I assumed the shape of the functions, but I knew that they cross actually at 1, 1, and I know that the x squared will eventually beat out the square root curve, obviously, because it's increasing much faster. So I knew that the square root curve was over the x squared curve in that interval, but you can check a graphing calculator if you'd like. So there's my height of the ith rectangle, and I multiply by the width. Okay? Again, you can sum up all these areas, take the limit as the number goes to infinity, but you're going to end up in the same place with that integral of the square root of x minus x squared dx. And that integral goes from 0 to 1. Okay, in the interest of time, I'm not going to calculate all of these integrals. Some of them will be more complicated, requiring your techniques of integration. Other ones will not be. Just a reminder on this one, the square root of x can be written as x to the 1/2 minus x squared, and you just use the opposite of the power rule to anti-differentiate. So this would be, what, 2/3 x to the 3/2 minus 1/3 x to the 3rd from 0 to 1. And that would be 2/3 minus 1/3, and then evaluating that as 0, still lose that, so that's 1/3. Hope I didn't make a mistake there. Looks good to me right now. All right. The most important part is the strategy, of course. That's always more important in mathematics. So what we're saying right here is that that area is 1/3. And a brief visual check, which I really enjoy doing. If I know this is the 0.11, does that little segment, that little slice, look like it's about 1/3 of that region? I'd say, yeah, it kind of does, right? If you look at that little block, that's a square. That's a 1 by 1 square with area 1, and yeah, that could be reasonably 1/3. Here's another one. We are to just simply write the integral, which measure the area bounded by that graph and the x-axis. Now that's a cubic, and I don't think too many people expect you to go back to Algebra 2 and find all the roots of the cubic and graph it, especially in calculus, we tend to reach for our graphing calculators when we're graphing, kind of complicated cubics like those. So we're going to grab our graphing calculators, and there it is. We really always need, when we're finding the area bounded by functions, we really always need to look at a picture. So there's my picture, and I think about sketching a little rectangle. Now, if you notice, the rectangle upper and lower, they change functions after 2. So I may have to write more than one integral at times. And there might be other ways around that, but for now, let's just write 2 integrals. And by the way, I will tell you, to check your roots, either on your graphing calculator or just plugging them in. But if you notice, y of 1 will equal 0, y of 2 will equal 0, and y of 3 will equal 0. So those roots are not lying to you in the picture. So the first integral that I'll write, upper minus lower, would be x cubed minus 6x squared plus 11x minus 6. That's my function height times delta x, or dx in the integral as delta x goes to 0. And that goes from 1 to 2. Then I can add on to it the integral from 2 to 3 of 0, my upper function there, 0, minus x cubed minus 6x squared plus 11x minus 6 dx. Okay? So that will work just fine. There is another way if you're doing it. If you are thinking graphically, you actually could do something with the absolute value of this cubic by flipping it up. Taking the absolute value would make that curve go up like that. And you actually could take the integral of the absolute value of x cubed minus 6x squared plus 11x minus 6 from 1 to 3, and that would work as well. But let's stick with the basics now. Upper minus lower for your curve height. And those are the integrals which measure the area. Another one, write the integral or integrals which measure the area bounded by the graphs of f of x equals e to the x and g of x equals 4 minus x squared. The 4 minus x squared, easy one, upside down parabola, up 4 units right there, like that. Crossing it to a negative 2. Not that that matters so much right now, but we have to get a little accuracy in. So that is g of x. And f of x is e to the x. So this one comes in here like this, crosses at 0, 1, and skyrockets off there. So that's f of x. Okay. So we draw our typical rectangle. Always draw a typical rectangle. We will set up the integral. The area of that rectangle is going to be g of x, upper function, minus the lower function. And here's where I need a calculator because I don't know where those two curves meet. And since we have an e to the x function and an x squared function, you will have to use technology to find the roots. So I'm going to label them A to B for now. And we could find those on our graphing calculator. I believe I have that over here. So my roots in this case would be negative 1.964 to 1.058. And then you could enter that directly on your calculator. I like to store them for my limits of integration and then just put A and B in there. And my final result is 6.427. Moving on, this is also possible to have functions in y. So life changes just a tiny bit if you have a function x equals y squared and x equals 2 minus y. Again, you always want to graph these. So if you remember, if you make, you can graph some points, or you can plug some in. But x equals y squared happens to be a non-function really, but it's a sideways parabola. It looks kind of like that. Okay, and 2 minus y, if x is 0, y would have to be 2. So I'm going to plot a few points kind of like that. And if x is 2, y is 0. So I've got something like that going on. I know it's a line, so I'm looking at something along the lines of this. Pun intended. Okay, so now the area that I'm looking at is going to be this area right in here. And I draw a little rectangle. But I noticed something. It's going to get a little complicated after this point of intersection, or even before it, because I have the same curve being my upper and my lower. Now that's possible because you can identify the upper function as y equals the positive square root of x there, and the lower function as y equals the negative square root of x. Okay, so I can do that for that particular range. So I will label that point A, and I'll set the integral up from 0 to A of the upper function, square root of x, minus the lower function, negative square root of x, delta x, oops, dx, sorry. I'm in the integral, so delta x is gone to 0. But then I have to add on to it another integral. This one will run from A to B. Call that B. And I draw my rectangle in there. And that rectangle will be the upper curve, 2 minus y, excuse me. Yeah, I have to solve for y. So y is going to equal 2 minus x because my thickness of that rectangle is delta x. So that will drive my choice of the variable. So it's my upper function of 2 minus x minus my lower function of negative square root of x. And that will go from A to B, which I would have to find on my graphing calculator. I'm just setting up the integrals for now. Obviously, we'd want to find A and B. So that's one way. It's kind of cumbersome this way. Okay. What's really nice is that Desmos, by the way, will graph non-functions if you enter it or ask it to, x equals y squared and x equals 2 minus y. So I did that, and I got a nice clean graph like this. So instead, however, in this particular problem of drawing vertical rectangles, what would be a little easier if your brains can handle it, and you should be able to, is to draw a horizontal rectangle. And the pathway is the same, okay, except for the fact now that the height of the rectangle, instead of upper y value minus lower y value, that height of that rectangle is going to be the right x value, which is that one over there. That's the right x. I'll label that right x, minus the left x. Okay. Now I say x's, but as you'll see, we're going to put those in terms of y because our thickness right there is going to be delta y. Okay, so the area of that one rectangle is going to be right x minus left x times delta y. But we're going to have to put that, both of those, in terms of y. Okay, so the right x here is the line. It's this one right here, which I know y is 2 minus x. The left x is going to be, no, I need them in terms of y. That's right, I need them in terms of y, so I'm good. I think we can leave them that way. Sorry about that. I was back to thinking the other problem. Okay, so I'm going to go the integral from that point, which I know is -2. It looks like -2 for now. I'm going to call it that. From -2 up to 1. See how my rectangles are going from here, from -2, whoops, from -2 all the way up to 1. I take my right x minus my left x, which is I'm going from -2 all the way up to 1. And I can see that if I put -2 in for y here, I'm going to have 4, which is the same thing on that curve. And if I put 1 in for y, I'm going to have 1 there, and I'm going to have 1 also there. So these are my points of intersection. I take my right x, which will be the blue curve, or 2 minus y, and I subtract my left x, which is the red curve, or y squared dy. And that is now the integral that I would evaluate to find this. It's a little easier if you can go sideways. The thing to know and to remember is you always take the right x minus the left x to find horizontal distance. That'll be helpful when you get into further applications of integration. So right x minus left x to find horizontal distances, and in this case they would have to be in terms of y because your thickness is in y. Okay? One last one. Set up the integrals to measure the area bounded by y equals negative x and y equals x cosine x. So I know that's the graph, and if you remember x cosine x, maybe you do, maybe you don't, that's a lovely stretch where the x curve is the amplitude of my cosine curve, which I put in here. I'm just going to lightly put in like this. So gradually my amplitude of the cosine curve increases as x increases. Since that's 1, it's going to be way up there, so I have this stretched out cosine curve. Kind of gets bigger and bigger and bigger. Okay, and this x would get negative, more negatively there, it would look like that. I have a better curve over here. Okay, so there's my x curve, excuse me, my negative x curve, and my x cosine x curve. Okay, which is right there in decimals. I've drawn 2 rectangles, and you can just set up the integrals. I think, let's see, yeah, I was given the interval that we want, negative pi to pi. So I'm going from negative pi to pi this direction, which happen to be the intersection points there also. If we set up the integral which measures this first region in here, area of that region, I'm just going to go from negative pi to 0. Upper curve is negative x, lower curve is x cosine of x. So negative pi to 0. That's going to be my area. Now, if you happen to know that what you have is completely symmetric, so if I know that the area of this yellow is equal to the area of the green, and since both of those functions are now odd functions because of that particular x there, since they're both odd functions, I do know that they are symmetric. I am going to just throw a 2 in front of that. You can always use symmetry to your benefit. Alternatively, you could go 2 times the integral from 0 to pi. Might be a little bit easier. X cosine x minus x dx. Okay? A little bit harder to manually evaluate because you'd probably have to use parts on x cosine x to analytically evaluate that. But that either one of these integrals will measure the total integral bounded by x cosine x and x from the interval negative pi to pi. Okay, hope this helps you finding areas between curves.